You are welcome to our last lecture for semester. We started verification in class. Oh, let me write it. Maths. Three, 8, 2. Dynamical systems. We have started verification in class. Is that okay? So today we are going to look. We have done sudden node verification. So today we are going to look at transcritical verification. Mama noise number. Transcritical verification. We learned that what verification is a qualitative it's a change in what? In the qualitative solution as the parameter is being varied. So here, if maybe we have a scalar differential equation with one parameter, then we can have what? Any of these three verifications. You can have one southern node verification. We can have transcritical verification, and then pitchfork verification. You get it? But for southern node verification, it's okay. It occurs when fixed points are created and at the same time or destroyed. Is that okay? That means that when we have our domain or the region of which our variables are defined, we realize that for a sub-range or for a certain values of the parameter, for a certain values of the parameter, we realize that two fixed points are created. Whereas for the rest of the values, we cannot get fixed point or the fixed point annihilates. That is when we have a southern node we have a southern node verification or tangent verification. Now today we are going to look at the transcritical. For transcritical, unlike a southern node verification, where the fixed points are created and also destroyed at the same time, here fixed points are not destroyed. Fixed points are created for all the parameter values. Is okay? The fixed points are created for all the parameter values. But what happens is that here there is a switch of stability. Maybe for a sub-range of the parameter, maybe we get two fixed points. Here two fixed points are created. Maybe x1 is a fixed point. Then another one, x2. That's the second fixed point. Is that okay? Then maybe if I take my alpha, because as alpha as the parameter is not necessarily alpha, maybe it can be psi. That's my parameter. A parameter is what? A quantity that has what? A range of values. So a parameter is not a constant, and it's also not what? Hello? Vidamante, can you hear my voice? So a parameter is not a constant. It's also a variable. A variable what changes. But a parameter has what? A range of values. Is that okay? Yeah, a constant has a fixed value. So here, if maybe let's suppose that the psi here takes the values. Psi take the values from, or is in the domain. Let's say 3 to 20. Maybe when psi is from 3 to 8, is that okay? Then the x1, the fixed point here, x1, becomes stable, asymptotically stable. And then x2 is unstable. Is that okay? Then, after 8, is that okay? When psi, maybe when psi is, or let me use this 3 to, this is open. Is that okay? Then when psi is in 8 is not part. Is that okay? But more than 8 to 20. Is that okay? Then the x1, which was what? Stable for psi what? From 3 up to a number before 8. Is that okay? For 3 what? Before 8. X1 is stable and x2 is unstable. But after 8, then the x1 becomes unstable. And then x2 becomes stable. Is that okay? So you could see that what? The x1, which was stable, I changed its stability from stable to what? Unstable. And then x2 has also changed its stability from what? Unstable to what? Stable. Then we say that there is a switch of what? Stability. And that's what we term as what? Transcritical verification. Is that okay? So for transcritical verification, the fixed point exists for all the parameter values, but what? There is a switch, is that okay, of stability between what? The two fixed points. So now we can start. We can solve an example. In this type of verification, the fixed point exists for all values of a parameter and can never be destroyed. And can never be destroyed. Thus, the fixed point exchange stability as the parameter is being varied. as the parameter is being varied. You get it? Yeah. So a prototype. So example 1. Discuss the stability or the deification of the x dt equals to alpha x minus x squared for all alpha x is in R. So this is a prototype. When you say prototype, it's okay, the general form of a transcritical verification. You see, it's a quadratic square without a constant. Is that okay? Yeah. So now, to find, or in order to know whether it verificates, all what we are doing is what? The qualitative analysis. So we have to find a fixed point and then determine whether the fixed point is stable or not. Is that okay? So here, let's find a fixed point. Is that okay? So to find the fixed point, put what? The x dt to 0. So what do we get? Alpha x minus x squared equal to 0. So x alpha minus x equal to 0. Then x1 equal to 0, or alpha minus x equal to 0. So x2 equals what? Alpha. You get it? Yeah. So look at this. We have two fixed points. And now, let's check what the stability of this fixed point. So we can we have to equate. Is that okay? F of x. Okay, the board, they can't see the down. Then let me bring it here. You can't see the down. Or alpha minus x equal to 0. So x2 star is 0 is alpha. So the fixed point are x1 star equal to 0 and x2 star equal to alpha. So here, once we know the fixed point, then we can let f, maybe f of x alpha, or simply f of x equals what? The function appear on the right hand side, or you make the derivative the subject, alpha x minus x squared. Then we find the derivative and substitute the values. Is that okay? Yeah. So here, let's differentiate. What do we get? F prime of x is what? Differentiate, you get what? Alpha minus what? 2x. So here at, is that okay? What's the fixed point? X equal to 0. Is that okay? At x1 star equal to 0. Then we put what? The fixed point into it. If it's less than 0, it is asymptotically stable. If greater than it is unstable. If it is what? 0, inconclusive. Is that okay? And we have learned the theorem behind it in class. Is that okay? Yeah. So here, f prime at 0 is what? Alpha minus 2 times 0. So alpha prime 0 is what? is alpha. Thank you. Like this. So now, obviously, I've got alpha. And this alpha, is it positive or negative? So here, now alpha, can we conclude alpha is positive or negative? It's okay, it depends on the values of alpha. And according to the question, we're told that what? The t equals to alpha x minus x squared. For all alpha x is in R. So alpha is what? It's a real number. So alpha is a real number. And looking at a real number like this, so 0, 1, 2, 3, minus 1, minus 2, even what? Minus 2.5, they are all parts. Is that okay? If you look here, when alpha is what? Is greater than 0. Look at this. If you consider what alpha greater than 0, then this is what? This is greater than 0. It means that the f prime at 0 is greater than 0. Then it is unstable. If you consider what alpha less than 0, then the derivative at 0 will be what? Less than, it is going to be asymptotically stable. And with 0, it is inconclusive. If I put it 1, greater than 1, you realize that what it is greater than 0. So do you get it? So here it means that any number or more than 1. Do you get it? So this one tells us that 0 is our verification point. Is it okay? Or 0 is the what? The separation. Is it okay? Separatrix. So here it means that we can consider this region alpha greater than 0 and alpha what? Less than 0. That will determine whether what our derivative or at a critical point will be 0 or positive. So we have to create regions. Is that okay? We have to create regions. So here we consider what? So we divide on alpha. Is that okay? We divide the range of alpha into two sub-regions. That is that okay? Minus infinity to 0 and 1. 0 to positive infinity. So you consider each case. Yeah, okay? Yeah. So now, this one, do they need to bundle? Do they bundle? Let's consider what? Region 1. That is alpha is okay, greater than minus infinity, less than 0. Is that okay? So if you are in this region, once alpha is what? It's negative. It means that there's an inequality. Alpha. So here, if I put my 0 here, minus 1, minus 2, minus 3, 1, 2. So here, alpha is what? It's less. Is that okay? Less than 0. So here. Is that okay? So that is alpha less than 0. So when alpha is less than 0, it's the same as this alpha less than 0, this region. We won't shade it because it's not equal to. So now, When alpha is less than 0, then alpha is a negative. So this is going to be what? Negative. So if you call it equation 1, then equation 1 becomes, then equation 1 becomes f prime at 0 is what? Negative. Is that okay? And this is what? Less than 0. So it implies that f prime at 0 is less than 0. So it tells us it is asymptotically what? Stable at 0. So here it implies that x1 star equal to 0 is asymptotically stable for alpha less than 0. You get it? Now we have to slot in what? The other one. x2 star equals what? Equals to alpha. Is that okay? So plug in x2 star equals to alpha into equation 1. We obtain, what do we get? F prime at alpha. F prime at x. What is the equation? It was what? Alpha minus 2x. Is that okay? Yeah, it was alpha. So it tells us f prime at alpha is alpha minus 2 alpha. So this will give us what? F prime at alpha will be what? Alpha minus 2 alpha is what? Minus alpha. But we are in the region 1. Alpha is less than 0. So again, what? 4. You get it? Yeah. Because alpha is negative. For instance, if you can pick minus 1 and put it there. Minus is what? Positive. Is that okay? So here, since what? Since alpha is okay. Alpha is negative. It's in the negative direction. Or since or in this region is okay. In region alpha less than 0. So f prime alpha less than tells you is a negative. So this is minus alpha, which is alpha. And this is what? Greater than 0. So it implies that f prime at alpha is what? Is greater than 0. In other words, because we are in the region this, alpha is negative, or you can just plug in the negative. Because some people have started complaining, I don't want any problem. Is that okay? So since we are in this region, so alpha prime minus alpha, we're going to do what? Minus alpha. Or if you wish, you could have put it here straight away. Is that okay? Or let me put it there straight away, so that you see you get a positive. So we are considering in region 1, alpha is less than 0. That's when alpha is negative. So alpha is what? It's in negative region. It's negative. So f prime minus alpha will go minus alpha minus 2 minus alpha. So f prime minus alpha will go minus alpha plus 2 alpha. And this is f prime at minus alpha equals to alpha. And this is greater than 0. So once it's greater than it is what? Unstable. Is that okay? So since f prime minus alpha is greater than 0, it implies that x2 star equals what? Alpha. Is okay? It's unstable. It's unstable. You get it? Or if you wish, you can say minus alpha. It's unstable. So now let's go to the other region where alpha is what? Alpha is positive. So we now consider this region 2, which is alpha greater than 0, less than or infinity, or alpha is greater than 0. Or if you wish, this once we are in a negative region, then this one becomes minus alpha. Is that okay? It's in a negative region, so this becomes minus alpha. So that here you put minus here. It doesn't matter. So in this region, then the x1 star is 0 and what? X2 star is what? Is alpha. We are in a positive region. We are in negative region. This is minus. Yeah. It is 0. Vidamante, it is 0. Randolph, Buedu, you have now joined. Hey. So our equation, our f1, f prime at all, x is what? Alpha minus 2 what? X. So we put each one. If we are in the Vidamante, if we are in the what? The negative region, we don't have negative. That's a minus what? 0. Is that okay? 0 is neither negative nor positive. It is 0. It's separate. It's like a separation. It's separate the negative what? Real numbers from a positive what? Real numbers. You get it? Yeah. So here let's continue. So we can now check the positive region. Is that okay? And the positive region at x1 equals what? 0. What do we get? F prime at 0 is what? Alpha minus 2 times 0. And so F prime at 0. Let me put that at the top there. Otherwise, some of you will complain that we cannot say. So here, F prime at 0 is what? It's alpha. You get it? And alpha, we are in a positive, alpha is greater than 0. Have you seen it? So this tells us that this is greater than 0. So alpha is greater than 0. So our derivative at the critical point, at the fixed point, is okay. It's greater than what? It's greater than 0. So this is what? Unstable. You get it? So now 0 has become what? Has become unstable, which was asymptotically stable previously. So it implies that x1 star equal to 0 is unstable fixed point. Unstable fixed point. Now, hey, so I cannot see your grandfathers. Where are the grandfathers? So now at x2 star equals what? Alpha. Then we put into equation 1. What do we get? F prime at alpha is what? Alpha minus 2. X is what? Alpha. So what do we get? F prime at alpha is what? Minus alpha. And alpha is greater than 0. Is that okay? So we have what? Negative or positive number is negative. So here, this is what? Less than 0. So it implies that f prime at alpha is what? Is less than 0. This indicates that x2 star equals alpha is asymptotically stable in this region. So now we can check the 0. Is that okay? So, Godfred Konbia, how are you? So now we can check the 0 at 0. What happens? So here we consider alpha greater than 0, alpha less than 0. So our f prime x is what? Alpha minus 2x. You get it? So at the point 0, at alpha equal to 0, what do we get? F prime at 0 is what? 0 minus 2 what? At 0. Realize that this is, I equated to x as alpha, sorry. So at the 0 here, if you pick what? X equals 0, x equals 0, alpha equals 0, you realize that what? You get 0, 0. What I mean is that pick x equals to 0, alpha equals to 0. What do we get? F prime at 0 is what? Alpha minus 2 times 0. So f prime at 0 is alpha. So pick alpha at alpha equal to 0. You know that you consider alpha less than 0, alpha greater than 0. So alpha what? When alpha is 0, you get what? 0. The test what? Test what? Fails. You get it? So where the test fails, that's your verification point. So here we realize that greater than 0, we get what? A fixed point. Less than 0 to we get a what? A fixed point. Do you get it? So here, when what? At the 0, it has failed. So we can use what? You can check the increasing and decreasing. And this is how to check the increasing and decreasing. This is 0 minus alpha. So we can consider few numbers, minus 1, minus 2, 1, 2. So check what? Positive. Is that okay? So here, equation 2 here. If you pick any positive number here, for any alpha greater than 0, any positive, pick 2 here. Here will be 2. So it is going to be positive. You get it? We have to pick the original function. What's the original function? F of x equals alpha x minus x squared. So when you pick any positive value, let's say x equals to 2, choosing, x equals, I've written 0. So f of 2, what do we get? Alpha times 2 minus 2 squared. So this will give 2 alpha minus 4. You get it? Now, if alpha is what? You want to know whether this side is increasing or decreasing. This side to increasing or decreasing. If I pick what? Maybe alpha value. If alpha is in this range, maybe 2, it will give me 0, 3, 4. 3 will give 6 minus 4. That is 2. So 1 is positive. It tells this one. It is increasing on this side. Do you get it? It's increasing on this side. Or we could have chosen a minimum or number. You could have chosen a minimum number. If I pick maybe a number which is very close here, 0.1 or 1, if you pick 1, this is going to be 1. This is going to be alpha minus 1. So when I pick a number like 2, or even this one, when I pick a number like 3, alpha to be 3, you realize that this is going to give us 2. So it is it is increasing on this side. So it's like this, increasing. And also when I choose choosing alpha maybe equals to minus 3, you realize that I will get let me pick the s first. The s value. If I pick s value minus 2, what do we get? F of minus 2 is what? Alpha times minus 2 minus 2 squared. So this is minus 2 alpha minus 4. So when you pick alpha, a small number here, maybe 1, alpha to be 1, the whole of this is going to be a negative, so less than 0. It tells you it is it is decreasing. So like this, it is decreasing like this. So always the verification point, you realize that it is half stable. Is that okay? The verification point. So now we have established that the 0 is the verification point. So it tells us, or where the test fails, it tells you that's the verification point. So the verification point is alpha equal to 0. That's what we consider alpha greater than 0, alpha less than 0. So now we have established that the exchange stability on the ground that when we considered alpha less than 0, the x1 at 0 was asymptotically stable. So now let's summarize. Let's summarize. We realize that for alpha less than 0, x1 star equal to 0 is asymptotically stable, and x2 star equals to alpha is unstable. Then for alpha greater than 0, we realize that x1 star 0 is unstable, and x2 star, or if you wish, can we make it minus, but in terms of magnitude, it's alpha. Is that okay? The same alpha. So this is the non-zero fixed point, and this is the 0 fixed point. So alpha is asymptotically stable. You get it? So look at this. There's a switch from stable to unstable, and here from unstable to stable. So we say that it undergoes a transcritical verification. Is that okay? Or even if you put a negative here, yeah, because for the fixed point, it becomes a negative when you have a negative axis. So this is the non-zero fixed point, and this is the 0 fixed point. So we realize that here we observe that the fixed point, we observed that the fixed point x1 star equal to 0 and x2 star equal to alpha exchange stability between them as alpha is varied from minus infinity to positive infinity. Hence, the differential equation dx dt equals alpha x minus x squared for all alpha x in R undergoes transcritical verification at alpha equal to 0. That's the verification point. But it's not always we'll be given a polynomial. Yeah, Anthony, I can do that. Why? Anthony Kojo Yaja. Is that okay? Yaja, I can do that. Don't worry. So let's solve one more example. But make sure that you protect yourself. You wear your nose masks, you sanitize. Do not spread COVID-19 to Dr. Barnes. Shakalu. So for transcritical, this is the geometry. This is the geometry. Transcritical verification. You see this? Unstable. Then this side. This side is stable. And then this stable, asymptotically stable. And this is unstable. That's transcritical verification. Millicent Cratton, you are late. Now, it's not always what we're given, or sometimes given a polynomial, or even sometimes given a transcendental function. Is that okay? Sorry. Sometimes given a transcendental function of which maybe you have to do something about it. Is that okay? So here, let's look at example 2, where we have a transcendental function. Let me look at the Shakalus and give you one of the Shakalu questions. Shakalu. Eesh. Look at this. Let me go up. or let me use AB. A. Hey, more question. I've tabled it. So here, show that. Let me change the top. This is an appropriate formula for a fixed point. That verification across level. Let me make it this. Show that. Show that undergoes transcritical verification at x equal to 0 when the parameters A and B satisfy certain conditions. Or discuss the verification of this. Albert Autry, you are late. Henry Isiama, Isaac Isiama, as well as Lydia Frimpong. Where is Stella Kwasa? Where is she? Out of carriage area. Then find an appropriate formula. Find an appropriate formula for the fixed point. That verification formula. Assume that parameters are close. Then leave that one. Stella Kwasa is out of the carriage area. Where is her sister? So now, let's look here. Juanita. It said that the x is equals to x into 1 minus x squared minus a1 minus e raised to the power minus bx. Have you seen it? Let's try to find a fixed point, whether you can get fixed point. So, to find a fixed point, put what? The x dt to 0. You put the x dt to 0, what do you get? X1 minus x squared minus a1 minus what? B minus bx equal to what? 0. Now look at this. This is what? X minus x cubed minus a minus what? A minus bx equal to 0. So can we get x? If you put what? X equal to 0. You get it, it will not satisfy. X equals 0, 0, 0. This should be 1. 1 times this. Pew. Have you seen 1 times this? This should be 1. So you get minus a here. So you don't get it. Now, have you seen it that it's not easy to get the critical point? The critical point is not feasible. There is no akugri. I think the television will turn off. there's information and the television will turn off in one. So here you cannot get a fixed point. Fixed point cannot be more ascertained. You get it? Because of the transcendental function. Transcendental function or exponential function. Is that okay? So the trick is that okay, or the clue is that anytime you have one exponential function, trig function, is that okay? Maybe hyperbolic function or anything of that sort, you have to what? Use the Taylor series. What? You write a Taylor series for that function. Is that okay? And truncate it. Maybe at the first term, second term, or third term. Depending on what you want. Is that okay? So here, if look at the prototype for transcritical, it is x, the x the t equals to alpha x minus x squared. This is a prototype. It's not the standard. So therefore, transcritical it ends at x squared, as well as what? As well as sudden node verification. And the sudden node, there is no what? There is no x term. Is that okay? That's the x, the t equals to alpha minus x squared. This is a sudden node verification. You get it? This is a prototype. So you look at the standard. Or even if the question was open, if the question did not tell you that should I undergo transcritical, then it depends on number of what the terms, your approximation. That will determine what the kind of verification you will get. It tells you that when you approximate, if you want to maybe the third term, that's the square, then means you can either get a transcritical or a sudden node. Is that okay? If you take it to a cube, that's a fourth term, then you are going to get on the pitchfork verification. Suppose that it is square, and we have the general quadratic equation, the x the t equals maybe alpha plus maybe x minus x squared, something like this. Is that okay? We call this one imperfect verification. Imperfect verification means that we cannot classify as what? As one of what? The elementary verification, that's sudden node verification, transcritical, and pitchfork. You can't classify as any of them. So in this case, we have to do some adjustments. Is that okay? And then get one of them. Yeah. So here, once it's a transcritical, it tells us that the highest power is what? Is 2. So I will have to truncate this Taylor series to the third term. You get it? I have to truncate it. So use the Taylor series to what? Approximate what? Search function. That is transcendental functions. Transcendental functions. Trig functions. Then what? Hyperbolic functions. Is that okay? Yeah. So all the transcendental function includes length and those terms. Is that okay? Yeah, can be. So the first thing we have to do is we have to what? Approximate what? This one, e raised to the power x, using the Taylor series. So using the Taylor series approximation, using the Taylor series expansion, we know this function, e raised to the power x. E raised to the power x is what? 1 plus x squared, 2 factorial plus what? K over so on. Is that okay? So if I have e minus bx, this is going to be 1 plus x coming from here. You get it? So what is here? Minus bx. Then this one was squared. So plus minus bx squared over 2 factorial. Because the transcritical, I will translate that as square. Do you get it? If I want to get pitchfork, then I'll go to the cube. So I will translate it here. So this is e minus bx equals 1 minus bx. Again, po shakalu ish over 2. Or plus 1, the error term, which is the cube. Plus the error term, which is the cube. The error term. You get it? So now I can call here equation 1 and here on equation 2. So I'll plug what equation 1 into equation 2. Hana emefa azunugu. Do you understand? So plug in equation 2 into equation 1. Yes. What do we get? Our dx dt equals what? X 1 minus x squared minus a 1 minus, let me even change this one. Pion C is shakalu. One minus what of this? 1 minus bx plus b squared x squared over 2 plus the error term shakalu. Hey, Isaac Esiama, you have come again. Perpetua Oliver Usu. Hey, Millicent Cratton, you cannot see. Are you sure? Just one. Cut it and one. Log in again. Millicent. And somebody advised me to keep the question. So this will give us what? The x dt equals what? X 1 minus x squared minus a. Then the whole of this, what do we get? 1 minus 1. 1 minus 1. Then again 4. Then this will give you negative. Is that okay? So minus b squared x squared over 2 plus my error term q shakalu. So pew pew. So what do we get? The x dt is what? X 1 minus x squared minus a, then b what? Bx minus b squared x squared over 2. Shamalai. Plus my error term q shakalu here. So what do we get? The x dt equals what? X 1 minus x squared. Then what do you get? Minus ab x. Again 4. Then plus a b squared over 2x squared. My error term. So I can ignore the error term. So I get what? The x, the t, let's expand. X minus x cubed. Is that okay? Then minus abx plus ab squared over 2x squared. My error term is what? Is a cube. Have you seen this? We say error term is a cube. In other words, the transcritical, the prototype of transcritical verification is what? When you say prototype, the standard is the x, the tail equals what? Alpha x minus x squared. What is up previously? So it means that I should end the highest point should be x squared. Do you get it? It's not if you have a power of 4, even powers, it's going to be still transcritical. Jennifer, you have now joined. Oh, Shakalu, I don't bear. Say, please, I don't understand. Jennifer, oh, sorry, you just came. It's okay. You, Stephen, look here. What is the, what we are doing is that the question said that we should show that this differential equation undergo transcritical verification. And for transcritical verification, there is an exchange of what? Of the stability. Is that okay? Exchange of stability. So here, when you say the sound is quite low, Jesse Annan. Let me go and call my technician. Boss, somebody is saying that the sound is low. I've called my technician. So here I say we should undergo transcritical verification. And transcritical verification exchange of stability between what? Two fixed points. So suppose we have x1 equals maybe alpha and x2 equals what? Beta. Maybe x1 equals to that. Is that okay? Or just x1, x2. Is that okay? What happens is that maybe if our parameter is alpha, our parameter is beta, is that okay? Then for some values of beta, let's say beta is what? Beta is in the interval of what? 1 to 10. Then maybe for 1 close and then 5 is not part. The x1 is stable. And then x2 is what? Unstable for those who just joined. Is that okay? Then after 5, for 6 or 5 open, 10 close. Then x1 becomes what? Unstable. And x2 becomes what? Stable. Have you seen the switch? Change over. Then we say that what? It undergoes what? A transcritical verification. Do you get it? That's the meaning of what? Transcritical verification. Then we say that there's an exchange of stability. It's like today. Is it okay? You are the richest man in the family. Is it okay? And then after 10 years, your brother takes over. You were rich yesterday, and your brother was poor. Now today your brother who was poor is now rich, and now you are poor. So there's an exchange. Is that okay? Between the two. Then we call it a transcritical. That means that we say that it undergoes a transcritical. As the parameter is changing. So it means that as the parameter is changing, the stability is that okay? The stability of what? The stability of the fixed point also changes. Is that okay? So when there's a switch between the two, then you say that undergo a transcritical verification. And transcritical verification, this is the standard form. It should be like this. The x power should be squared. Here can be plus or minus. Is okay? And then the other term should be x. It should be a constant. We know that the general quadratic equation, quadratic equation is what? F of x equals to ax squared plus bx plus c. Is that okay? So for a transcritical verification, if c is equal to 0, what do we get? We get what? F of x equals what? Ax squared plus bx. Oh, I've forgotten that some of you will not see. At the end of the day, they will be typing. Shakalu, I cannot see. So if you have f of x equals what? Ax squared plus what? Bx. And we know that mathematics, we can divide through. Is it okay? Or if I equate even this one to 0, we can ax squared plus bx equal to 0. So if you have this dividing through, is it okay? Plus b over a or x equal to 0. So when we have this one on the right hand side of the differential equation, that the x or the t equals what? X squared, something like this, plus b over ax. Then it undergoes, can be plus or minus, it undergoes what? Transcritical. This is a transcritical verification. Is that okay? And for a sudden node verification, it's when b is 0. Have you seen it? But if a, b, and c are non-zero, then we cannot classify as well as a sudden node verification, transcritical verification, or a pitchfork. Is that okay? Then we say that it's what? It's an imperfect what? Verification. Do you get it? That's an imperfect verification. So here, because the question is saying that we should show that it is undergo a transcritical, then our Taylor series approximation, we know the standard form. The standard form of what? Transcritical verification, or the standard. That we call the prototype, the standard form of transcritical verification. Transcritical verification is what? The x what? The t equals to alpha x minus x squared plus or minus. So it means that we should end at a power of x squared. But we have a power of x cubed. It means that we have to ignore the x cubed. So even if you have x raised to the power 4, we have to ignore. X raised to the power 5, we have to ignore. Do you get it? Or even look here, we say our error term is what? It's x cubed. So we have to ignore. You have to change the video quality to 720. Thank you. So here, this is the standard form. So you have to ignore this term. So our dx, dt. And here, anytime your right hand side, look at the right hand side here. The equation here, there is what? Exponential function. Is that okay? So always, in order for you to what? Study the verification, this should be a derivative, dx, dt. And this side should be a polynomial function. Should be a polynomial function. Not any function. Is that okay? So you should have derivative on the right hand side. And then this side should be what? A polynomial function. So you have to ensure that there is a polynomial. If they look at this, this is a polynomial function, this is a polynomial function, this is a parameter, and this is not a polynomial function. So if you don't have a polynomial function, then you have to use the Taylor series. You have to approximate that word function by the use of what? The Taylor series. Is that okay? So suppose I've given you this. Maybe something like x squared plus x plus sin x. Once this one, you ask yourself, is this function, is this function, or is it a polynomial function? Polynomial function. Is that okay? If no, it's not a polynomial function. So we have to use the Taylor series. You have to use the Taylor series. You have to use the Taylor series. Is that okay? To what? To approximate this one. And then come and add. You get it? What happened to the new online platform they developed? Perhaps it could be streamed there for free. Do you get it? So anytime, any of the time which is not a polynomial function, you have to approximate using the Taylor series. That is why we have approximated the exponential function here. So here, what do we get? So you have to ignore this one. So the x dt equals x minus abx plus ab squared over 2x squared. So you can factorize the x. So the x dt equals what? 1 minus abx plus ab squared over 2x squared. Look at this. Now it's in the standard form. Have you seen it? Because the standard form, the standard form of transcritical verification is what? The x dt equals alpha x plus or minus I squared. You get it? Have you seen x squared? Do you get it? Do you get it? That is why we should use the Taylor series to change it to polynomial so that we can do our routine work. Is that okay? So once you have a polynomial, now we can find our critical point or the fixed point or the equilibrium point and then study the stability of these fixed points. Is that okay? And check whether they switch the stability or not. If they switch the stability, then it's a transcritical verification. So now we can find a fixed point. So let's call here equation 2. So to find the fixed point of equation 2, put the x dt to 0. Ajua Kwanedu, where is she? Out of coverage area. So here, what do we get? It implies that 1 minus ab x plus ab squared over 2x squared equal to 0. If Ajua Kwanedu has logged in, you should comment. Is it okay? You should say yes, Bob. I'm present in the class. So now, what do we get? We can factor x out. So here, 1 minus ab, then plus ab squared over 2x equal to 0. So x1 star equal to 0. Is that okay? Then 1 minus ab plus ab squared over 2x equal to 0. You get it? So here x we got ab squared over 2x equals to minus 1 minus ab. So this will give us x is what? Minus 2, is that okay? Then 1 minus ab over ab squared. For all, is that okay? ab squared should not be equal to 0. We can even push the negative inside. Is that okay? Yeah, let's push it inside. So x2 star will be 2. Then if I push it, this will be minus, this will be plus. So b minus 1 over ab. Oh, sorry. Some of you will not see. So here, x2 star will be 2 ab minus 1 over ab squared. For all ab squared should not be equal to 0. So now our differential equation we had was what? Was dx dt equals what? 1 minus abx 1 minus abx in plus what? ab squared over 2x squared. So we let what? This be a function. Let f of x equals what? 1 minus ab x plus ab squared over 2x squared. Now we differentiate. Is that okay? Carol, do you understand? Roll call Piney. Who is Piney? Oh. So now, look here. Let's differentiate this. F prime of x. What do we get? Differentiate. We get 1 minus ab plus. This will what? 2ab squared x over 2. We shall carry 2. Is that okay? So f prime of x is what? 1 minus ab plus ab squared x. So the fixed point, our x1 star equal to 0, and this. So now look at this. You want to study the fixed point, but we should know the verification point. But normally it is when we are looking for verification point, then what? It will bring the fixed point. Is that okay? Hey, Opoku, Brefi, Emmanuel, Shamalai. Yes, Shamalai. Say it again. What that? So at x1 star equal to 0. What do we get? F prime at 0 is what? 1 minus ab plus ab squared times 0. So this is f prime at 0 is what? 1 minus ab. Have you seen it? Have you seen it? We can classify whether this is negative or positive. 1 minus what? Ab. And we were told that a and b are real numbers. Akugri, is that okay? Is that okay? They are parameters. So it tells us that for us to know whether this one is less than 0 or greater than 0, then what? We should know what? Whether this is less than 0 or greater than, we should divide what? The interval of this. Is that okay? Into sub-intervals. Do you get it? You have to divide, because we can see that the one will be the verification. Because if AB maybe equals to a number like 2, then 1 minus 2 is what? Minus 1. It's negative. Have you seen it? If AB is 3, then 1 minus 3 is what? Minus 2 is negative. If AB, let's pick a negative number, maybe minus 2. What do we get? Then what? 1 minus 2. We get what? 1 plus 2, which is what? 3. Then it's positive. But if you pick AB to be 1, 1 minus 1 is what? Is 0. That's where the test failed. Into normally where the test failed is what? Is the verification point. You get it? Carol, I don't see the relevance in what you are teaching. Because you are not in level 400 to do the application. Is it okay? Yes. And verification has a lot of what? A lot of applications in our society. You get it? That's a lot of applications. Example of verification, lighting of what? Matches. Or if you take disease, infectious diseases, like now we have a coronavirus, there's a COVID-19, coronavirus, and this coronavirus, how do you get what the dynamics of it? People who are coming from outside, how do you know the total number of people in Ghana that will contract? Even those who came in, that we call it the diffusion aspect. And we can analyze whether or it verificates. If verificates, the solution changes. So here we have so many types of like hub verification. If it's a hub verification, it tells you that it occurs seasonally. Is that okay? And we have diseases like that, which occurs seasonally. That is where you don't see the relevance of it. Those pure man will not give you anything. You will not see the cital distance. We are now building our mathematics. Is that okay? So that those who are interested will come and do what? Mathematical biology. That's where you apply these things. Is that okay? I appreciate it. So here, we could see that 1 is what? Is a verification point. So 1, we can see that AB equals 1 is the verification point. It means that we should divide our region based on a 1. Is that okay? Who rained off there every 21 note so that you go and choose. Say is rained off. Hope your baba too much. So here, once 1, we have identified 1 is a verification. So 1. Then maybe 2, 3, 0, minus 1. So you can consider when AB is greater than 1. Is that okay? And AB less. So it tells us that this equation 3, we have to consider when we have to consider the region. Or we can even clean this and say, well, now for region, I don't want to clean my function here. Is it okay? I don't want to clean my function. So let me call this one 3. So it tells us that now we have to consider the regions. So let me write this one up here because I'll be using it. So for region AB greater than 0, what do we get? At x1 star equal to 0, f prime 0. We go on AB, so we have to redo this one again. Then f prime at 0 is what? 1 minus AB. But AB is what? Or AB greater than 1. Sorry. AB greater than 1. We can even pick any value. So choosing maybe AB equals anything greater than 1, maybe 2. What do we get? F prime at 0 is what? 1 minus 2, which is what? Minus 1. And this is less than 0. You get it? Any value in the region, 1 is satisfied. That is it. Is that okay? So it implies that x1 star equal to 0. It's what? Asymptotically stable in this region. Stable. Then we go to what? The other one. Hey, Shakalu. People talk. So now at x2 star equals what? 2ab minus 1 over ab squared. What do we get? We put it here into equation 3, or put into what? Equation 3. What do we get? F prime at 2ab minus 1 over ab squared is what? 1 minus ab plus ab squared times what? 2ab minus 1 over ab squared. Pion. What that? They are in the same region. So here, what do we get? Prime at 2ab minus 1 over ab squared. We will get 1 minus ab. Then this is what? 2ab minus 2. So f prime 2ab minus 1 over ab squared. We get what? 1 plus ab minus. Even this one we can subtract. What do we get? Minus 1. Minus 1. Then plus ab. Now in the region, ab is what? Greater than 1. So even if I pick ab to be 1.1, we get positive. Have you seen it? So choosing simple for simplicity, ab will be 2 or greater than 1. What do we get? We get 2ab minus 1 over ab squared equals what? Minus 1 plus 2, which is what? 1. And this one is greater than 0. It tells you what? It is what? Unstable. So it implies that x2 star equals what? 2 in the bracket ab minus 1 over ab squared is unstable. You get it? Carol, what we are doing is the COVID-19. Because you haven't started learning what? Mathematical you haven't started learning applications. Is that okay? That's level 400. Mathematical biology. Go and open any book. Shakalu. And the stability we are doing, all the differential equations, these are applications. We need these things. Otherwise, differential equation is what? It's a sham. And it's not only disease models. We are applying fluid dynamics in engineering, electric circuits. Is that okay? Electric circuit, Ohm's law, Faraday law, and those things. We model differential equation. We find that our our fixed point and determine whether they are stable or not. If maybe it's electric circuit and you find your fixed point, they are stable, it tells you that your current is stable. It's okay. It will not fluctuate. If it's unstable, it will fluctuate. Do so. That's it. That's why you're learning dynamical systems. Because you haven't seen applications. As are now, some of you, your network, then it will go, then it comes, and you will complaining. That is unstable we are doing, and that's what we are doing. Instability. That's what we are doing. So it means that when we employ as a matter, this is what we are going to do. Shakalu. Awara. So now, look here. We had what? Region 1, 2, 3, 0, minus 1. And we consider what? AB greater than 1. Then we have to also consider AB what? Less than 1. So 1 is a verification. You get it? Yeah. So here, now we consider this region. AB less than 1. Is that okay? So for region AB less than 1. You can even go online and see. Go and type mathematical model of COVID-19. See a lot of papers using differential equation. What we are doing. You see a lot. So now we can even summarize here. Is it okay? For the first region, when AB is greater than 1, what happens? When AB was greater than 1, AB greater than 1, x1 star is what? Equal to 0 is what? Asymptotically stable. And x2 star equals what? 2ab minus 1 over ab squared is what? Unstable. Is that okay? So once I've written that, I can even come here. So in region AB less than 1, that's this 1. X AB less than 1, 0, minus 1, 2, 3, minus 2. So our f of x, so putting x1 star equal to 0 into what? Equation 3 yields, is that okay? F prime at 0, 1 minus AB plus AB squared times 0. Kaloli, your comment is making me laugh. Even myself, people are reading pure man, they want to run into applied. Even by lecture, stability, they always come and say they have regretted. F prime at 0 is what? 1 minus AB. You get it? But we are in a region where AB is less than 1. So any number less than 1, 0, minus 1, minus 2, minus 3. Simple, I can pick 0. 0 is less than 1. Have you seen it? So choosing AB. AB equals 0 to me, all of them are 0. Maybe minus 1. F prime at 0 is what? 1 minus 1. Again. Greater than 0. Have you seen it? Now it is unstable. It implies that x1 star equal to 0 is what? Unstable. So it has changed from asymptotically stable to unstable. X1 star equal to 0. Is that okay? Then putting the second one, putting x2 star equals what? X2 star is what? 2ab minus 1 over AB squared into equation 1, 3. Shakalu. F prime 2 AB minus 1. AB minus 1 is okay. 1 AB squared. 1 minus AB plus AB squared times 1. 2 AB minus 1 over AB squared. Pew, pew. Away. 1 minus AB plus, let's expand, 2AB minus 2. Pew, pew. Shakalu. Minus 1. Minus 1. This one plus AB. But we are in which region? AB less than 1. Is that okay? AB what? Less than 1. AB, we are in a region AB less than 1. It could be. So any number less than 1. Let's pick even, we can pick the same, minus 1. Is that okay? Shakalu. So here, choosing AB, so minus 1. Put it here. 2 AB minus 1 over AB squared minus 1 plus minus 1. Paul ne is what is ne? Shakalu. 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 Asymptotically what? Stable. It's asymptotically stable. 2AB minus 1 over. Let me even conclude it here. Shakalu. Shakalu. Is asymptotically stable. For AB less than 1. Now exchange your stability. Is that okay? Exchange your stability. So we can summarize our results. Let us summarize. So summary. AB greater than 1, x1 star equal to 0 is asymptotically stable. Star is unstable. Now AB less than 1, Shakalu. X1 star is unstable. X2 star is asymptotically what? Stable. Is that okay? So look at this. Switch. Pew. Pew. Asymptotically stable to unstable. Unstable to asymptotically stable. So what? Transcritical. So you conclude. So we we observe that the fixed point, you have to conclude, is very important. Point x1 star equal to 0, x2 star ab minus 1 over ab squared. Exchange. Change stability between them as AB is varied from minus infinity toward positive infinity. Hence, the question, what is it? The x dt equals to x1 minus x squared minus a1 minus b minus bx for all what? A, b, x in R undergoes transcritical verification at AB equals to 1. So we have ended the lecture. It's okay. I could agree. What? Your mom said that it's getting late. You should come and cook. Jennifer what? Typed. Said, please, my mom said it's getting late. I should come and cook. Oh, do you know how to cook? Shakalu. I will cook for you to eat. Come here. You will even bite your hand. Shakalu. Goodbye. Father. Chief. When is it good?